Welcome to the second day of the RISE camp. Can you hear me well in the back? Yeah, great. All right, so today we're starting with a security session, and after that we have a talk on AirDosh, a platform for self-driving cars, and then we have a talk on our serverless efforts. So on the security side, in this session, we're going to tell you about the significant direction we're taking in the RISELab, and that is secure collaborative learning. And we're looking at this direction from two angles: federated learning and coopetitive learning. So the problem setup is quite simple. You have N organizations that have sensitive data that they cannot share, yet they would love to train a global model over all of their data in the hopes that the model will be better on the aggregate than their own local model on their local data. So, for example, fraud detection is a great example because criminals hide their traces across different banks. So to detect fraud effectively, the banks would have to train a model together on their aggregate data. However, banks are in competition because of customers, so they cannot share their customer data. Similarly, the situation is for money laundering, actually human trafficking, sex trafficking, and all of these are still primarily detected through financial forensics. And without these banks being able to compute on their joint data, they cannot detect such very important violations. So the question is, how can they compute the model without sharing the data? And this problem shows up in many forms. For example, medical, right? So how can we compute the best cancer treatment across different healthcare providers, which cannot share data because, well, the data is sensitive, so there's privacy regulations or concerns. Here's another example. You might want to compute predictions, not necessarily training, in a collaborative way. So you can have a home monitoring system that records private video streams from someone's home, and they're so private that ideally you wouldn't send them to the cloud. The data are being sent to the cloud so that they can be analyzed by a model, for example, a deep learning model, which produces predictions such as, oh, the baby woke up, or there's someone at the door. And there's a lot of problems with privacy violations and hackers attacking these devices who are connected to the internet and so forth. Okay, so ideally you wouldn't send all this private video stream to the cloud, but then you can't put the model at the customer either because it's a sensitive model, it's the business model of the company. Okay, so you're in a situation where the cloud cannot share the model and the home user doesn't want to share the video. Okay, so you want to collaboratively compute the prediction. And yet another example is where you have, let's say, an aggregator company that has a bunch of other organizations as customers. Many of your companies are in that situation. And they want to train a model across the different customer organizations to provide better service. Okay? But again, without collecting all their data. Okay, so this problem shows up in many cases, and I'm sure that if you think about your own situation, you'll find a bunch of such use cases. We're already working with many of you on use cases. So we termed a term for this, namely coopetition. So it stands for cooperation plus competition, which is exactly what happens here. You want to cooperate to train something together, but you're in competition, so you don't want to share the data. This term actually already existed in the business literature, so we borrowed it for this scenario. So by coopetitive learning, we mean learning on the data from multiple organizations without them sharing data with each other. So I'm sure you heard about federated learning. Google, for example, has a lot of really nice protocols on this and some of the early work on this. And you're wondering what's the difference, right? How are they connected? So there's some differences in setup, but really the primary difference is security. So in terms of the setup, usually in coopetitive learning, the parties all compute together in a decentralized way, whereas in federated learning, usually there's an aggregator that aggregates and trains the model by aggregating information from the different parties. Now the setup is not so important, the difference, because you can kind of have both setups in both cases, but what's important is that the security is very different. Federated learning is much weaker in security and coopetitive learning is much stronger. So the reason why it's weaker in federated learning is that parties share intermediate data with each other, in addition to the final model. Okay, so they want to train a final model together, but in the process, they're sharing a lot of intermediate data. For example, the way things work for federated learning, let's say deep learning, a party sends a model update, so you have iterations. Each party computes on their local data some model update, like a summary of their data, and sends it to the aggregator. The aggregator aggregates all these updates from the different parties and computes a new model, it's an intermediary model, and then sends it to the parties. Okay? And now the parties have this new model, can compute new updates, and this process repeats for thousands of iterations. Okay? So in this process, the aggregator learned a lot of information about the parties. It learned all these model updates, thousands of them. Also, the parties learned intermediate models, okay? And there's papers showing that there's a lot of leakage in this scenario. So federated computation existed for a long time. For example, federated databases were, there's a whole literature on that. And their security was never really a goal, right? They were collaboratively computing and they were hoping to reduce the bandwidth that they send from one database to another to improve overall performance, okay? So in some sense, federated learning is great for bandwidth, but not so great for security, yet as Google points out, it does reduce, in many cases, the amount of information you send to the aggregator. You don't send the whole data of a party. Now, in contrast, in coopetitive learning, you don't share intermediate data at all, okay? So the only thing that the parties will learn is the final model, and no intermediate data. The only data that's being shared in the process is in encrypted form, and the parties cannot decrypt it. They compute on it with special cryptographic algorithms. I'll mention a little bit about them in the talk. But the point is that they only get to share the final model and no intermediate data. With that, stronger security also comes slower performance, so federated learning is faster. And there's a lot of interesting hybrid mechanisms between the two. So in the RISELab, we actually work on both directions. I would say the more significant one we focus on is coopetitive learning, because we're trying to provide these very strong security guarantees, but we're working to provide practical protocols. And for a number of different scenarios, we already designed such schemes and systems that can provide practical performance. So let me give you a sense of how we do coopetitive learning. We take two approaches. One is cryptographic, and one is trusted hardware. It turns out there's a trade-off between them, and there isn't one winner in all cases. Okay? It depends a lot on the use case. So in the cryptographic setting, we are working in a paradigm called secure multi-party computation. So this paradigm existed for 30 years, but in all these 30 years, there's been so much progress in faster and faster schemes, and the progress is really, really admirable. The idea is that the organizations exchange encrypted data, okay? So they don't send summaries in clear text. They just send encrypted data that they cannot decrypt until the very end. Each organization computes on the encrypted data, and out comes an encrypted model that they can then decrypt and share with each other, okay? But in the process, even though it sounds like magic, I mean, the math enables this, in the process, the parties don't get to see each other's data. And this is not, you might wonder if this is fully homomorphic encryption. This is not fully homomorphic encryption because that's too slow. This is a co-design of all kinds of different crypto tools, like garbled circuits, secret sharing, some partial homomorphic encryption that are tailored and work well for particular types of workloads. Okay, so we put them together in a meaningful way. So obviously the main challenge there is performance. So for example, there are platforms out there that can compute any function with secure multi-party computation, such as speeds. So in particular, you can train any model using them, but it would be very slow. So for example, if you train a linear model on I would say, medium-sized data set, it took us 3 months. I mean, estimated because the machine runs out of memory. Instead, our approach in the RISELab is to really take advantage of our strengths in the 3 areas of system, machine learning, and cryptography, and co-design them together to improve performance by orders of magnitude. So for example, we choose a better machine learning formulation that fits the cryptography better. We design tailored cryptography, and then the system planners and compilers to exploit the cryptography. So for example, this year, pointing here, we had a paper called Helen, which can train linear models in much less time. Okay, for the same data set and the same security level, it improved by almost 3 orders of magnitude. Okay, and this is for a very, very strong performance, very, very strong security model. If you want, lighter ones, then you have even faster performance. All right, so that was the cryptographic approach. In terms of the hardware enclave approach, for example, leveraging enclaves like Intel SGX, a very, very, very quick primer. So hardware enclaves provide a hardware-enforced isolated execution environment. So you have the processor, you have the die on top of it, and inside it, there's decrypted data. But there's a memory encryption engine that encrypts the data as soon as it leaves the die. So all the data in memory is going to be encrypted. Now the processor can compute on decrypted data as before, so that gives good performance. But as soon as it goes out of the processor, it's encrypted. And this protects against a very strong attacker, because even if the operating system were to be compromised, or even if an attacker were to have root access, or have compromised the entire software stack on a machine, they cannot see what's inside the processor. Okay, you have to do, theoretically, a very strong hardware attack that's not clear how to do without destroying the secrets. So here's how we would do coopetitive learning with hardware enclaves. And we already do this in the opaque project, which I'll mention soon. So each organization is going to send encrypted data to a cloud that has enclaves. Okay? Only the enclaves can decrypt the data inside. The cloud only sees it in encrypted form. Now these enclaves can perform the learning task and train and then obtain the model, and then they can share the model with the parties, maybe send it back in encrypted form, or they can just release it publicly, depending on what organizations want. So you probably heard that SGX has a bunch of side channels, cache timing attacks, branch predictor-based side channels, page fault-based side channels, memory bus side channels, and so forth. But the cool thing is that if you design your algorithms to be so-called oblivious, then all these side channels that I mentioned go away, okay? And by oblivious, what I mean is that the way you access memory in your algorithm is not when you need it. It's according to a predefined schedule that is independent of secrets, okay? Because what these side channels exploit is not the data in memory. The data in memory is encrypted. They're exploiting the memory addresses you're accessing. But if you're designing your algorithm to be oblivious, your memory addresses are predefined and fixed. So in the RISELab, we are designing all these learning algorithms and analytics algorithms to be oblivious. Okay? So think about the AES instruction in hardware or in or AES or basic crypto implementations in OpenSSL. They're already made oblivious and side channel free. Well, similarly, we make learning tasks and analytics oblivious so that you don't have to worry about a wide range of side channels with SGX. All right, so this brings us to summarizing our 2 approaches, cryptographic and trusted hardware. As I mentioned, none wins in all settings. It really depends on your setting. So with cryptography, it's nice that you can just start running it. You don't need special hardware. It's all in software. But with the trusted hardware, you need to have hardware enclaves. You need to have trust in the hardware vendor. Now, that's not so bad these days anymore because we have cloud offerings of hardware enclaves, such as Azure Confidential Computing. Also, to buy, many of the modern Intel processors have enclaves on them, so they're not necessarily more expensive. But for the cryptography, you do need to compute across the different parties. You can't just send it to one cloud. It has to be decentralized, and it's going to be slower. Whereas with the hardware enclaves, you could potentially run it all in a cloud or decentralized, depending which way you want to do it. And in many cases, it's faster. Okay, so it really depends on the setting that you have and what performance you're willing to tolerate, what hardware requirements you have, and so forth. All right, so let me give you a sense of the projects we have built and are building. So we're calling this effort the MC² stack, so multi-party collaboration and coopetition. Okay, so you can easily remember this because it's the energy formula. And so basically we're going to push our different projects as part of this repository for MC². So we just released this repository, so it's new, just basically announcing it right now here. And we pushed one first project, which will be demonstrated in the tutorial, so federated decision trees, as part of the repository. And soon we're going to push our other systems that we've been building. So if you're interested in this space, then watch this GitHub. So to give you a sense of the stack, what happens is that the goal with MC² is to export a Python DSL, so a Python interface, such that any non-expert system developer who doesn't have to understand hardware enclaves or cryptography, they just write the learning task in Python. And then they can write different applications that they care about on top of this Python interface of MC², whether those are fraud detection or anti-money laundering, private inference, medical research, and whatnot. Now, inside MC², we have different types of projects, some that work on top of cryptographic tools, others that work on top of hardware enclaves, or others that are just federated learning, so they don't need any special crypto or hardware enclaves. And a developer can simply set the idea is to set a bit, whether they want to do the computation with cryptography or with hardware enclaves, or just federated. So on the cryptography side, I already mentioned Helen, which can train linear models in a very strong security model. Besides this, we've just recently published a camera ready for Delphi, which can do deep learning inference, okay, between a cloud holding a model and a user having, their own input vector, okay, without sharing the data with each other. Now you're going to hear in the next talk from Wenting about Cerebro, which can take a generic Python DSL and compile it down to cryptography, to a cryptographic execution. And Cerebro is nice because it can plan for you that execution to give you good performance, as opposed to just using some state-of-the-art, being fixed to using one state-of-the-art library that in some cases can be very slow. Moreover, Cerebro supports some interesting policies. So we've had, many of you say, oh, I train a model with other companies, then it turns out the model really helps them, but it doesn't help me. I wish I hadn't done that. I wish I can take it back. Well, with crypto, you can actually do that. So with Cerebro, you can train a model, keep it encrypted, then you can test it under encryption, see if it gives you an accuracy on your testing data that you're happy with. And if every organization is happy with that, they can release it. Okay? So in Cerebro, you can specify all kinds of interesting release policies when you want to release the model out of the encryption. Or you can specify privacy policies, such as, let's add differential privacy to the final model so the final model doesn't leak something about an individual user. Okay, so you can do all kinds of policies like this. You can express them in Cerebro, and Wenting is going to tell you more about Cerebro. Now, on the hardware enclave side, we released 2 years ago Opaque, which can do analytics, so complex SQL queries. These are useful, for example, for feature engineering, or just in general, if your workload is analytics. And this is already on GitHub, and a few of you have already used Opaque. Now, this year, we've also just made available the camera ready for Civet using security, which basically runs Java programs inside enclaves. Also, we pushed, the first project we pushed as part of MC² is the federated XGBoost. So we heard from many of you that one common machine learning tool you're using is XGBoost, which is decision trees training. So we made that federated, and you'll see a tutorial in this session on that. And that is already pushed as part of the MC² project. Next you're going to hear about, from RISELab about how to make it coopetitive, okay? So how to go from federation to coopetition for XGBoost and provide stronger security at hopefully, still very efficient execution. So by the end of the year, we're hoping to push a few other projects in the MC² repository. Delphi, which is the deep learning inference. Cerebro, which is the planner and policies. The coopetitive XGBoost. And Civet, which is the Java execution in enclaves. All right, so this gives you a sense of the overall platform. The way it fits in the RISE stack is that it goes from execution all the way to platform, and we're also working on how to integrate it with Ray. All right, so in conclusion, RISELab MC² stack enables federated and coopetitive learning for organizations having sensitive data. This is a new repo that's available here where you can watch for the different projects that we're pushing. And let's collaborate. So we would love to hear about more use cases from you, or if you're interested in any one of these projects, then contributing on it. So come and talk to us. Thank you. All right, so the next talk is going to be by Wenting, and she's going to tell you about Cerebro, which you can see it here in the stack.